Number 7 in section 6.1 looks fairly straightforward to me. They've given us two functions right here, and I hope we can tell looking at this. The blue function I have here, f of x, looks like it's a downward opening parabola, whereas the green function, g of x, is an upward opening parabola. And they're asking us just to find the area between these two regions right here. So we're going to go ahead and graph them to try to get a sense for where this thing exists. And as fun as it would be to graph that by hand, I think we're going to go ahead and run to the calculator and let that do the work for us. So I'm going to add a graph page right here, and then let's see, my first function right here, f of x, was, I had it here just a second ago, oh, looking at the wrong thing, here we go, f of x here was 20 plus x minus x squared. All right, gotcha. So here we go, and we'll graph that, and whoa, that's higher than I thought. I guess it makes sense, its y-intercept would be 20. Okay, and then let's put in our second function here, which is going to be g of x, x squared, at a minus 5x. Now, I was expecting to see 2 points of intersection here, and I think we've got them. And boy, the graph really kind of helps me out here. It really looks like they both intersect at the ordered pair 5, 0, but then there's this other point of intersection over in the second quadrant that looks like it might be a little bit tougher to find. So, I feel pretty confident about that 5, 0 here. So let me go ahead, you guys, and let's draw, let me take a look here real quick. Yeah, that blue parabola was just a little bit off center and way off to the right there. So I'm just going to get a rough sketch of what was going on here. Its vertex looked like it was up here somewhere, and that downward opening parabola looks like it's going to do something like that, whereas the green parabola was opening upward, looked like it passed through the point 5, 0 here as well, and that vertex was going to be, gotcha, I'm just trying to get a sense for what that looked like here. Wrong way. All right, and our second point of intersection was going to be up here somewhere with a vertex down here. So this graph does not need to be perfect, everybody, but I do want to try to get the points of intersection roughly correct. So I'm pretty sure this point right here was 5, 0, but I'll verify that in just a second. I do need to know the coordinates of this point right here. So we're going to set these two functions equal to each other. And I guess if I did all this work, guys, I could just let the calculator analyze the graph and find the points of intersection, but I like to get my practice in when I can here, guys. I'm going to set these two functions equal to each other here. If you're good at what you're doing here, guys, and if the solutions work out nicely, it's probably faster to factor this thing. I'm going to bring everything left and get a 2x squared. That'd be a minus 6x, and a minus 20 is 0. Pull out a 2, x squared minus, yeah, I feel good about this, minus 10 is equal to 0, and that's going to factor into an x minus 5 and an x plus 2. So we're going to get points of intersection at x equals 5 and at x equals negative 2. That 5 here tells me that I was right, that the x coordinate right there was 5, and I think if I plugged real quickly a 5 in here, 25 minus 25 would be 0, 20 plus 5 is 25, minus 25. Yeah, this point checks out. But what I didn't know is that the second point of intersection, this one right up here, now looks like it has an x-coordinate of negative 2. And I'll plug that really into either function to get the y-coordinate. Negative 2 squared is going to be 4. Negative 5 times negative 2 is positive 10. So that'll be a 4 plus 10. Looks like we've got a negative 2, 14 for that point. And if I look at the graph real quickly here, 20, 18, 16, yeah, that looks good to me. Okay, so we've got those 2 points of intersection, and we now see the region, let me start messing with that a little bit. Okay, we now see the region that we're trying to find the area of, and it's between these two curves right over here. Now, the first thing we're going to need to do with any area problem is decide whether we are going to integrate that area with respect to x or with respect to y. Now, given that both of these equations, I'll use that word, were given to us in function notation, that means they're both solved for y in terms of x, it would certainly be a lot easier if we could integrate this thing with respect to x so that we didn't have to turn around and solve the equations for x in terms of y. So if I were to just think about a couple of my vertical rectangles, maybe there's one, maybe here's a second one right there, maybe here's a third one right over there somewhere, I like what I see. All three of those rectangles are bordered on the top by the blue curve, which is f of x, and they're bordered on the bottom by the green curve, which is g of x. I don't think we have to deal with any changing boundaries here. So that makes this problem, as I said earlier, relatively straightforward. So our area then is going to be found by taking the definite integral, and we said with respect to x, of the top function minus the bottom function. Now, I've tried to say this to you guys in class as much as I can. When the functions are already defined for you, it's perfectly fine if you guys want to take some shorthand right here and say that the integrand is just going to be f of x minus g of x. If you want to put this in for f of x and this in for g of x right here and right here, you certainly can do it, but there's really no need to do it, guys. It'll speed things up a little bit if you just use that shorthand, as long as you have clearly written on your paper somewhere what f of x and g of x are defined as. Or, on the case of a worksheet or maybe a test, if f of x and g of x are already defined for you on the paper, you don't need to write them out again. The only thing missing in my integral is my limits of integration, which need to be the lowest and highest values of x in this region. So this region begins at a minimum x value of -2 and ends at a maximum value of 5. That is as much as we're going to do to set this thing up here, guys. And I do think this is an integral we probably could do by hand, but most of the time when you guys see a problem like this, especially with relatively big numbers, this is going to be a calculator active problem. So let's get working on that. Now, the other thing to notice here, guys, is that if I go back to my graph, I already defined what the problem called f of x for me is f1 of x, right? Oh, sorry. What did I do? You go away. Here you go. f1 of x is this definition that I'm moving around right here. And then my g of x is f2 of x. I can use that to my advantage as well. Let me show you what I mean. So here we go, guys. We're going to hit, you're going to hit menu 43, menu, calculus, and an integral. We're doing a region that goes from -2 up to, and we said 5. Gotcha. And now, f of x minus g of x. Well, on my screen, I've got that as f1 of x. There you go. Close it off. And then minus g of x I had defined as f2 of x. Now, one nice thing about this, guys, is it kind of avoids the potential mistake that people make sometimes. When you're subtracting a polynomial minus that f2 of x, you need to remember to put parentheses around the g of x. People sometimes forget that. They forget to distribute their negative. Okay, we're going to integrate all this with respect to x. I think we're good to go here, guys. 343 over 3 is the answer that my calculator gave me. No need to round that to a decimal, guys. Both myself and the AP graders were perfectly fine with fractions right there. So 343 over 3 is the answer we came up with. Now, if I want to think quickly about whether or not that answer is realistic, let's go ahead and just quickly mull that out right there. 3 goes into 343. Oh, I don't know. That's probably about, what, 115 times almost? That would be, what, 345 if you triple that. Yeah, so I'm going to say it's approximately 115. Now, if we were going to think about this yellow region here in terms of a box that I could draw around it, this shouldn't be that hard to figure out. The width of this box, it goes from -2 right here to +5. So the width of that box is 7. Now for the height here, guys, let's take a look here. It looks, I'm guessing right here, guys, but if this y-intercept right here was 20, I'm guessing this box goes up to about 21 on the top, and this box, I'd played around with this idea before, I think is somewhere in the neighborhood of like -6. So from -6 to 21 gives us about 27 for the height of that box, and 27 times 7, not the easiest thing in the world, but 49, carry your 4, that's about 189. So if the area of this whole box right here is in the neighborhood of 189, does it stand to reason that the yellow portion is about 115? Well, it definitely would need to be less than the 189. It looks to me like a pretty sizable portion of that purple box is shaded in yellow, definitely more than half, I would say, so I feel pretty good about this answer. Then when I look at the solutions manual, I feel really good about this answer because they've got 343 over 3 as well. So that's it, everybody. That's our answer to problem number 7.